In this video, we are going to discuss an inequality that follows from Taylor's theorem and that still remains valid for vector functions. Okay, we have seen before Taylor's theorem. I copied it here for real functions. Okay, and we have also seen that Taylor's theorem, we have it here, it says that we can approximate a function f that is n times differentiable, but by a polynomial, Taylor's polynomial. And in particular, when I take this Taylor polynomial of degree 1, okay, what I'm writing down here is precisely the mean value theorem, which we saw in the previous video, that can be extended in some way to vector functions as an inequality. So what we are going to do, we are going to extend this theorem as an inequality for vector functions. This is, by the way, problem 20 in chapter 5 in the book. So, looking at the theorem, Taylor's theorem, it gives us an idea of what we need to show. Okay, so here we want a function, a vector function, f from AB to RK, all right? And we want a function to be, let's copy the hypothesis, is precisely the same hypothesis. So we want it to be continuously differentiable n minus 1 times, and we want to have an nth derivative that exists for all t in the interior of the interval AB. Okay. So this is what we need. And then once we are able to show that, a similar result is going to hold. Okay, so we define the Taylor polynomial just the same. The only change is that now we have a vector function. So this is actually an array of functions. Okay, and then for some beta in AB, we are going to have that the difference, that's what we can say now, the difference between f and p, by the way, p is now a vector 2, in modulus is less or equal than the absolute value of f at some given point x, okay, the nth derivative of f divided by n factorial b minus a to the power n, b minus alpha, I'm sorry. Okay, so that is what we want to prove. So here, for some x in AB. So here what we are showing is, if you want, it's an error estimate just like the one we had for the case k equal 1. We can box this that we are going to prove. And then the idea follows very closely to what we did for the mean values theorem. Okay. Here we are going to take z. If we look here, okay, the left-hand side gives us an idea of what we need to consider as z. Okay, so it's f of b minus p of beta. Okay, so we call that z for convenience. And then we are going to define phi of t, which is a vector function. Sorry, not a vector function. Precisely that's the point of the proof. It's the product of f of z times f of t. Okay, there we go. So here the point is that phi of t needs to be a real function, otherwise I will not be able to rely on what I know for real functions. Okay, so that's the whole reason why we are doing this scalar product, this dot product. All right, so once I have defined it this way, then I can apply Taylor's theorem, okay, and say, well, phi of beta minus the Taylor's polynomial for phi at alpha, around alpha, evaluated at the point beta by the theorem. And here we are applying the theorem for a real function for one variable. Okay, this is beta minus alpha to the power n divided by n factorial times the n derivative at some point x. And because I'm taking the modulus here, I'm putting the modulus here too. Okay. All right. So then here I can write what is the n derivative. Notice that the function phi depends on t only through f. Okay, so z is constant. So when I apply the product rule, the derivative of z is going to be 0. Okay, so better for me, beta minus alpha to the n divided by n factorial. And then here I have z times the nth derivative of f at x. There we go. Okay, so on this side, I think this is all we can do. So let's work a little bit also on the left-hand side. So phi of beta minus p phi alpha. Okay. What is this? So this is z times f of b minus p of phi alpha beta in absolute value. Okay. So we need to figure out what is this, what is the expression for this p phi alpha beta. So let's go here. Okay, let's write it down carefully and let's see what can we say. We want it at beta. Okay, so if it's for phi, I need to put phi's wherever I have an f. It's at alpha, that's correct, and then evaluate it at beta. So this is what I'm looking at. But then the same remark that I did before applies here, that the kth derivative of phi, okay, looking at how it's defined, it's going to be z times the kth derivative of f at alpha. Okay, again, because z doesn't depend on any variable, okay, it's constant. So if I plug that in this expression, let me do it a little carefully. Okay, here I can factor out the z. Okay, the z here, I can factor it out because it's constant. and does not depend on k. Okay, so this is f of k alpha over k factorial b minus alpha k. Okay, nice. And if we look at what we have here, that is precisely the definition of p. Okay, so this is z times p vector p evaluated at b. Again, notice here that this p is a vector polynomial. All right, so yeah, with this information, now we can do much better. So this is z times fb minus, and now I write down what I got, z times p at beta, factor out the z, and notice that this is the definition of z. So what I have here is the modulus of z squared. This is very much the same as what we were doing for the mean value theorem. So let's recollect what we have. Well, actually, I only need these two pieces. Okay, so we have already proved this, and we have just shown that the left-hand side equals z squared. All right, so, well, I think it's clear now. We have z here, and the only way I see to connect these two is to apply Schwarz's inequality. Okay, so then I have the modulus of z times the modulus of the n derivative, and simplify. And then, using the definition of z, f of b minus p at beta less or equal than beta minus alpha to the power n divided by n factorial times fn x for some x in the interval x in alpha beta. Here, this should be beta. I think we need to correct since the beginning. Yeah, but here it's beta, but it's okay.